So here's the first slide here. Tonight we're going to talk about, a lot of you guys know this about our DBJ1 antenna. That's our dual band J-pole base antenna. So it appeared first in QST back in 2003. So it's been around for 17 years as a concept. We did a roll-up version of it in 2007. And then our latest article was in 2017, which is the tri-band version of it. So we'll talk about how we developed the dual band version of it tonight, and then there's another talk if you want to hear how we developed the tri-band one. That's another 40, 50-minute talk. So here's the two original articles. The one on the right is the original base. That was the DBJ1, standing for Dual Band J-pole 1, back in 2003. And then the roll-up version, which one of my students suggested, says, could you make a roll-up version of your DBJ1? We call it the DBJ2. That's not a talk, but I'll show it to you later. It's pretty much the same concept, except we readjust it to make it in a roll-up. More of a mechanical challenge than it is an electrical challenge. And then our most recent one is this one here. That appeared in 2017 in QST. So that was 3 years ago, and that picture was started taken 4 years ago of my daughter there. She's now a graduate student in engineering over at Boise State. She's a mechanical engineering with electrical engineering minor, KJ62XM. I talk on DMR all the time.
Hey, Ed, just one moment.
Yes.
Your audio's a little bit low. Does everybody else have the same thing?
I think. Is it okay with the rest of you folks?
Is everybody hearing Ed okay?
Yeah, fine.
Mayor, I'm okay.
Yes.
Okay, thank you.
I can hear him fine. Okay, I'll leave it. If it's too soft, interrupt me again. I can always raise the audio. I have this on automatic. Hey, I have it on one of these. Here's my cool studio microphone, man. It's a really...
Oh, wow.
Oh, it's got a shock mount and everything on it.
Oh, look at that.
Oh, it's far superior. I found that the audio quality is far superior to that of the built-in microphone.
Hey, Ed.
Yeah.
I don't think you're actually using that microphone.
Oh, that's why. Hang on. Aha. You are right, because...
Now how does it sound?
Hey! Oh, yeah.
Oh, I'm
Much
glad
better.
you pointed that out. Yes. This is an automatic. Does this sound like studio quality audio?
Yeah, much.
Sound very Heilish. Sound very Heilish.
Yep. That's right. That's a really nice element in here, too. So, okay. Oh, thanks. I'm glad somebody pointed out. Yeah, the other one is on the camera, and that's like 2 or 3 feet away, and it's some cheap thing that comes with the camera. All right. So, that's my daughter there, and she's a grad student now, and knows much more about her field, which is falling particle receivers, than I do any day. She's taking courses that I never took, really heavy tensor analysis and stuff like that. You know, at some point it's interesting. At some point you come to the conclusion, now you're getting way beyond me, so I can't help her with problem sets or anything unless it's something electrical in nature. Okay, and then eventually we had to patent some of these antennas. Not that we wanted to, but because people were copying. The original design I had, within a year, I saw people selling them on eBay, versions of it, and it wasn't even the right material because we make ours out of a special 300 ohm twinny that we special order. And they were doing it with 450 ohm because that's more common. But turns out that doesn't work very well for UHF because it's just too wide. And I would buy some of these just to see how they were, and we didn't see a single one that performed to our standards. They just took our dimensions, and you can't take our dimensions. You're using 450 ohm twinny. You're using different material. So I said, well, I don't like that. I don't mind ham clubs building it, and I would help them, but I don't like people copying it and some saying, this is the Ed Fong antenna for $25. I didn't like that. So the university attorney, Mike Kaufman, at times says, you got to patent all the other stuff you come out with. You've got to patent it. Otherwise people copy you, and you don't have any recourse. So we did not patent the original antenna. It was too late. You're only given like 12 months of publishing a paper to patent it, and we missed that by quite a bit. So all the subsequent ones, like the tri-band one, we also have one on how do you get gain? How do you get gain out of a collinear or J-pole antenna? And it isn't a Slim Jim. You know, people say, "I think you got with a Slim Jim." No, you don't get 6 dB gain. It's a little bit more elaborate, like what's shown down here. And that's another separate talk if you guys want to hear that. Steve may have heard that already. I gave that over at FARS. Okay. So why a J-pole? I kind of like the J-pole configuration. I think a lot of you guys use a J-pole too because there's no radios. You know, we grew up with ground plane antennas with radials, and you know, I would make it out of a SL239, flip it over, and put a 19-inch copper wire, number 16 or so, that would hold up, solder on some radios on the little holes of the SL239. The thing would work. You know, back then I didn't know a whole lot about antennas. You figure the thing resonated, SWR is low, must have a good antenna, right? Well, it turns out it's okay, but really a better antenna is a J-pole, and that's why in the end, these days, most professionals even use some form of a J-pole configuration. It gives you much closer to an ideal dipole, but more importantly, it's end-fed. And we'll show you this in a while. You feed it at the end. I think the next page here. Here's a picture of Mount Sutro. Took this about 2 years ago when I went up there. Look at it. There's no antenna here that I could see. There might be one or two. There's no antenna these days with radials, which means they're not of a ground plane or a dipole configuration. They're probably most likely, if you tore them apart, they're J-poles. Now so the advantage of it is no radio sticking out. Of course, the disadvantage is they're going to be taller. A J-pole is a half-wave radiator and a quarter-wave matching stub. So you're talking 3/4 of a wavelength tall. So that's quite a bit taller than quarter wave. It's 3/4 of a wavelength. In fact, 3 times taller than a ground plane, but you don't get radials. Now, but the other thing, I think a lot of people choose the J-pole, or the reason for them to choosing is it doesn't need a lightning arrestor. It's a short-circuited antenna. This is a DC short. So if you put an ohm meter between the center and the shield, it's a short. You know, maybe not 0 ohms, but close to 0 ohms. That's a real advantage because it cannot charge up. It's a DC short to the shield. And that's exactly what a lightning arrestor does. You know, when you talk about a ground plane or a dipole, that's an open circuit in air. In fact, I think I have a picture of it. Here's like a dipole. Here's an old dipole mounted. Look at it. You have to center feed it. You have to center feed it up 1/4 wavelength, down 1/4 wavelength. And it's an open circuit. There's a little insulator right in there. It's an open circuit. So if there's a lightning somewhere close by, this part can induce very high voltages. Nowhere to discharge it but your radio. That's not good. Even if this were to induce 30 volts right down your radio, 30 volts, good likelihood if you don't have any good protection, it will burn out the front end or at least burn out the diodes. So that's why you need, in series with this type of antenna, likewise with a ground plane, some type of lightning arrestor. That's another $20, $30. For commercial grade one, a little bit more, but hams can get the cheap ones for $20 or $30. I'll show in a J-pole later. You don't need that. Well, I'll show it right. Well, no, I'll show it in a while. I'm just trying to tell you why I like the J-pole. So no lightning arrestor. So I saw this back in the 1990s, early 90s, because prior to that, all of us use ground planes. You look in QST, ground plane, or dipole of some kind. Whatever shows it, you know, in QST or in the ARRL handbook, that's what we tend to use. Except by 1990s, these J-poles, these copper Js, I guess that's the most popular one, copper J, and then these ribbon Js that I'm going to show you today started showing up. Same configuration, just different implementation. And what I found when I got a hold of one of these back, this was 30 years ago now, 30 years ago. I got it from Denny Monticelli, AE6C. And I took it home, and he had it in a roll-up with using Radio Shack Twin Lead. And I tell you, the thing actually worked quite well. I was impressed by it. It's simplistic, long, 3/4 of a wavelength, but it worked quite well. And when I saw this, I said, hey, you can actually make a base station antenna out of this just by sticking into a very PVC pipe, 3/4 inch. And by then, the PVC pipes by the 1990s had been pretty well perfected in terms of UV light and durability. You know, the first generation of PVC pipe was really lousy. it would turn yellow, and after a few years you'd step on it and it would crack. But by 1990s, they had it pretty well perfected. It's the same plastics they had perfected for the 30-year vinyl windows. It's pretty much the same material. And they're absolutely right. I've had the stuff for 20, 30 years. It does not yellow anymore. It stays durable. It doesn't crack. Of course, I hear there's another problem. Now you can't get rid of this stuff, right? It won't deteriorate in nature. It never breaks down. But anyway, I did that back 30 years ago, and wow, it worked pretty well. It really worked pretty well. So I'll show you how we dual band that simple antenna. And to date, we've delivered well over 18,000, probably 25,000 by now, both commercial and ham. And we think for the simplicity, if you do it right, it actually performs quite well. So, but the topic of discussion tonight here is, so how do you make it dual band and have it work properly? This came about because by the late 1990s, 2000, there's a lot of J-poles out there, a lot of dual band radios, right? Those Alincos and ICOMs started coming out, dual band mobiles, dual band handhelds. But a lot of folks had single band antennas they had made. You could buy a dual band antenna like who would make them? Comet would make them. Diamond, we had the GP50s and things like that. And Diamond X50s. I mean, that may have been out by then. But then you're talking good money, $100, $80 to $100 for higher performance one, maybe $150. So knowing hams, you walk up and down the flea market and say, "Hey, I've got a J-pole. Can we ever make it dual band?" Well, a lot of folks notice that, well, mine kind of already works dual band. Yeah, it kind of works dual band. You put an SWR meter on it, and it's acceptable, right? But they found if you get the single band J-pole, I'll show it to you some of these J-poles like this, copper J, you would find an arrow one, and it would work. It would work even on UHF. Well, it kind of works. The SWR is pretty low, low enough where it wouldn't blow out your radio, which is good. But what they found was in actual performance, you can hit a repeater because the repeater is pretty strong. But you start actually using it on simplex, maybe emergency operations. What people found is it performed pretty poorly. And if you actually quantified it and simulated it on a simulator, it's about 6 to 8 dB loss of a standard antenna, of a standard J-pole at UHF. So if you get a VHF antenna and operate it at UHF without any special apparatuses, it loses about 6 to 8 dBs. It will resonate. The SWR is not the problem. It'll resonate. It just won't perform very well. The resonance comes about if you do antenna theory. Most antennas will always resonate at its odd order harmonics. It's just, if you were taking my class, you could see how we do the waves and everything. So, for example, if it's a 100 megahertz antenna, it will get dips at 300, 500, 700, 900, etc. At least to the point where your coax and everything is still performing. So usually, if you have 2 meters, the coax you're using, it should perform up at UHF, 3 times the frequency. So that means a VHF antenna, 150 megahertz or so, will resonate at 450, third harmonic. You'll see a dip. The problem is the pattern won't be quite right. Most of the energy will go up in the sky. I'll show you here. Here's a slide, the 2 slides forward. See, we did this on EasyNet. This is an EasyNet simulation, but you can do it on ADS, FETCO, any of those simulators. So a vertical dipole would have a pattern. You guys have probably experienced hams to recognize that that's the fundamental pattern for a dipole at the fundamental. That's what you want. But what you will find is at UHF, or the third harmonic in this case, the actual pattern will look like a 4-leaf clover. Now again, in this, if you recognize this is the sky, this is the earth, this or the bottom of the earth here, and this is the ground level. Here's the transmitter, you're standing right here. So if this is ground level and you're standing right here at sea level, here, if you do it the third harmonic, then this is the sky here, a good part of your energy goes up into the sky. You're just catching a little lobe there. And what is that little lobe, if you were to quantify? About 25% of the energy. It's about 25%. If you were to actually calculate the area, about 75% of the stuff is up here and about 25% is here, and you're standing right there. So unless you're up on top of a mountain or an airplane, this antenna doesn't do you real justice, because 75% of it goes up into the air at 45 degrees angles. So what we would like to do is fix that. We would like to get this pattern, this fundamental pattern, both at VHF and UHF. So I concluded if I wanted to do this successfully, I would have to modify a J-pole. I wanted to stay away from the ground plane because I like the J-pole because it doesn't need a lightning arrestor and has no radios. But whatever I did to it, it had to be pretty simple, reproducible, no radials due to the wind load. No fancy inductors, right? Even if you could do it, if you got to get some fancy silver-plated inductor, forget it. That's not a useful design. Not for something to be published in QST. No fancy capacitors. And by the way, that's a general rule. If you see an antenna, with the exception of maybe HF, if you guys have ever dealt with HF traps, they're pretty hard to build efficiently, even at HF. And really at UHF, it's very difficult. You might get resonance, but in terms of performance, you can't get reasonable capacitors at UHF that are fairly consistent and can handle high power. They tend to vary. If you ever look at capacitors, chip caps, 10, 20%. Well, then it's not reproducible then for an antenna. If it's 10 or 20% off, that's just, the variance is just too much. And plus they have, by the time you get to UHF, pretty lossy. Capacitor might have inductance elements. They're just not very reliable. So I couldn't use those. No inductors, no capacitors, because they're not very easily reproduced. And if you could, sometimes pretty expensive to buy. So I tried all types of configurations. So basically, what did I come up with here? So here's the pattern. So this is what I thought about. What would work? Well, antenna designers love to use the Smith chart. They love to use the Smith chart as a tool. The only thing you have to understand in the Smith chart for this discussion is that here's a Smith chart. It is 0 ohms on the left and infinity on the right. And it represents, when you start here and move here, that represents a quarter wave. So 180 degrees represents a quarter wave. 360 degrees represents a half wave. So it takes a half wave to go all the way around and a quarter wave to go halfway around. And the reason why you want to understand this is it says if I start out with a short circuit stub of any kind, and I'll get the short circuit stub. I'm sure I have one here. Hang on. Here, I got some here. Here you go. Here's like a quarter wave at UHF, so it's about 5 inches. And what you have to understand, and I think a lot of you guys are experienced hams or engineers, if you short one end, and most of my new students will fail this question, if you short one end, what's the impedance on the other end? Not the DC resistance. The DC resistance, if you short one end, is going to be 0 on the other end. The DC impedance depends on frequency. In fact, if you go a quarter wave, in this case a quarter wave, 5 inches, you're going from a short circuit, go up about 5 inches, and it should read maybe not infinity on a network analyzer, but pretty high, thousands of ohms. It's got to be thousands of ohms. That's what happens. And if you go another quarter wave, it will go back to short. Or one could say, if you start with an open, if you start out with an open circuit, you start here, and if you move a quarter wave, believe it or not, it's going to be a short. So that's something antenna designers really try to build on. We use this all the time to match impedances. So we're going to do the exact same thing here. So let's move on here. So here's the basic ribbon J. Ribbon, because you make it out of 300 ohm twin lead, you really don't need that piece there, but you cut a notch. You cut a notch, and this is how it works. Here's half wave, 37, 38 inches, whatever exact frequency you're going to have. And so normally you would interface it or connect it to right in the middle there. you would interface it right there because that's the 60, 70 ohm mark. And like that dipole we saw, you have a piece of coax go right at it 90 degrees and it will work. But the problem is, physically, when you do that, not a whole lot of people want to build that. Physically, that means you got to put an arm, which means you got to put a mask up there, and then you have the coax run down, and that coax tends to disturb the pattern a little bit. But that coax running down really disturbs the pattern. I mean, it's got to be pretty far away not to disturb the pattern, a couple of wavelengths. And you're not going to have that because then the arm has too much torque. So it's not a very convenient design for a vertical dipole. It can be done, but you have to you got to interface it right there, connect to something 90 degrees, kind of far away so it doesn't interfere. And because eventually you got to bring that coax down somewhere, it will affect the pattern because it's parallel with that half wave. So that's why this J-pole is pretty clever. You look at it, basically, here's the half wave, which means the low impedance here, but it's a high impedance there. It's a high impedance on the corners. So all you have to do is interface it with a high impedance. That's where this quarter wave stub comes in. Remember, a short circuit at the bottom, that's 0 ohms. Short circuit, 0 ohms at DC, 0 ohms at 150 megahertz. But as you move up a quarter wavelength, it's going to go around the Smith chart and go higher and higher impedance to a point where at a quarter wavelength, it will be a high impedance. Hopefully impedance that will match the end of this dipole, which is also a high impedance. Now the first question people ask is, it's 15 1/4 inch, 1 1/4 inch. You do your math correctly, that's 16 1/2 inches. Shouldn't it be about 18, 19? Yeah, it should. But it's in twin lead. That's an air. When you hear 18, 19 inches, that's an air. This is twin lead. So in the twin lead, the wave will not travel at the speed of light. That 18 inches, by the way, comes from a very basic formula. No calculus or anything fancy like that. C is equal to F lambda. The speed of light has to equal to the frequency times the wavelength. And see, when you build normal dipoles in air, you use the speed of light. C is 3 times 10 to the 8th meters a second equals frequency times lambda. You enter the frequency and it gives you the wavelength. That's an air. But if you're trying to calculate stubs, you can't quite do that because, again, the wave that you're dealing with does not travel at the speed of light in that material. It's always a little bit slower because the material slows it down. And that's called the velocity factor. Velocity factor is the speed of light is 1. Certain coaxes are like 0.85, 0.8. That means it slows it down by 20%. So in this case, in twin lead, I think it's like 0.85 or something like that. So it comes out not 18, 19 inches, but about 16 1/2 to be optimum. So again, this is a short. You go up a quarter wave. It's maybe not infinity, but several thousand ohms at least. Several thousand. That matches the end of a half-wave dipole, which is also not infinity, but several thousand ohms. So it's a pretty good match. And then, of course, if it's short there, and if it's very high impedance there, common sense would say, well, it's got to be 50 ohms somewhere. And 50 ohms is probably closer to 0 than it is to infinity. So you notice, instead of being up here, it's more down here. And it turns out, typically, it's between 1 and 1/4 inches. I mean, you can simulate that, but you can, when we initially did it, we just did it by experiment. You can get a SWR meter, you can get these SWR antenna analyzers and find that spot just by experimenting. Because if you move it closer down here, it's going to be closer to 0. Move it up here, it'll be closer to infinity. So that's how you find that spot. Then you can confirm it, right? If you measure the SWR in the end, you can confirm, hey, it's pretty low. That must have been the spot where it's 50 ohms. So here's, using that concept, you'll see numerous folks using that basic theory and making a real practical antenna. Here's one. It's called the Copper J. Very popular back in the 90s, 2000, 2010. You still can find it today. I'm sure if you type in Copper J on eBay or QRZ, you will find somebody either making one or selling one. I think the only problem is if you actually need to make one of these, it'll work. It's pretty expensive. Copper's not cheap anymore. But by the time you finish off this with a cap, a T, an elbow, and another cap, you're in just copper alone at least $20. And it will work. How do I know it works? Because we built one. Here we go. because we have built them just to see how other antenna configurations work. And this one works fine. Now, you can't quite use it at UHF as well. I'll tell you why. Because this is the transmission line you're building. And at UHF, to act as an efficient transmission line, you need these closer together because it's higher frequency. You know, at VHF, you're okay. You know, VHF quarter wave is like 18 inches, and this is probably only about, little under 2 inches. So it still looks like a transmission line. Because quarter wave, you know, you figure as a rule of thumb, quarter wave is 18, you can probably get up to 1.5, 2 inches and still kind of get away with calling this a transmission line. But what you can't do is, you can't do it at UHF, because at UHF, a quarter wave is 6 inches, and that's 2 inches. What happens is that just starts radiating at UHF. This portion is close enough to an antenna where you start losing a lot of the power. And it's also in the wrong direction. It's horizontally polarized instead of vertically polarized. So I think if you use this at UHF, you would find it, very quickly find that it's not performing quite up to snuff. But at VHF, we found that it's pretty good. So that's the Copper J. The same configuration. We're using just different material, just different implementation. So to solve I noticed is to solve this dual band problem here, again, this one won't work that well at UHF, but if you were able to use like twin lead, yeah, it'll resonate at the third harmonic. But I'll show you another cool one. Arrow makes this one to try to cure the UHF problem. Because remember, if you use a VHF antenna at UHF, you will lose about 75% of its performance. That's too much. You know, if you were to lose 20, 30%, that's probably acceptable. You start losing 75. Not only is it very noticeable, it's just too much. You might as well just stay with your rubber duck at that point. So Arrow comes up with a pretty good solution. This is it here. They did this about, probably 15 years ago. I don't think 20, about 15. One of the clever engineers says, why don't we do this? Here is the 2-meter portion. So 57, 60 inches or so, 19. So this is an air. They don't have this in dielectric, so it is going to be 19, between 18 and 19 inches, depending on what part of the 2-meter band you want. So that's the VHF 2-meter portion. And then in this antenna, they kind of parallel it. Here's the UHF portion. They use this as the main radiator, and they stick a little 6.5 inch piece in there. Again, it's in air. It's not in a dielectric, so it won't be shorter. So at UHF, here's the antenna at UHF, but at VHF, it takes the whole thing. Now, there's only one problem with this. This is a pretty good improvement. We have one of these, of course. Here, let me show it to you. Had to buy one, right? When you're in this business, you got to see what people are doing and test their actual performance. Not bad. I think if you play around with the matching, it's a pretty good match, decent. The only problem is you have only one feed line. So let's say you're at UHF. At UHF, remember, it still sees a low, this antenna, the VHF part, still sees the low impedance at UHF. So it sees two antennas. If you plug in a UHF signal that has a good low match, it sees this part, and it sees this part. You would like all of the energy to go into this part at UHF because that's the proper antenna. But there's nothing to prevent part of the signal to going into the VHF part because it also presents a low impedance. In fact, let's assume that both are pretty well matched. Theoretically, half of your signal at UHF will go in the proper one, and the other half will go into the improper one. And the improper one, you lose about 75%. So what can you say?
Question.
Yeah.
How do you hook the coax up to this? I don't understand.
They figured a very clever way, and it works. This one actually floats, or we'll call it the ground, and it's connected right to this one. And then this is insulated. There's an insulator there, and that's your driving point. It will work.
Huh.
So your center conductor actually drives this, and the shield sees this and sees that.
Oh.
And yes, it will see a reasonably low SWR. Not perfect, but reasonably low.
Driving it off the 19 and a quarter element on the bottom.
Right. You see, it doesn't matter. In RF, it doesn't matter which one you do. I don't know, like in a dipole, you can flip it. It doesn't, theoretically, you can flip it. It doesn't matter. But yeah, but to look at it, you could say this is the driving element. But what resonates is, at UHF, is this element with here. And of course, 50% of it also resonates there because it's the third harmonic. And if it's a 2 meter signal, what resonates is between this element working off this 19 and a quarter inch element. So it works. Except half of your power is going into the wrong section. The other half is going into the right section. And the part that's going into the wrong section, well, 25% of it still works. So it's not bad. I mean, if you actually have to experience this for a while to say, it doesn't quite work as well as I would like. It's a few dBs off, but it's not that much off. I mean, it's not like 6 dB off. So that's the Aero solution, that UHF. This one does not work at UHF very well. And then we have the Slim Jim, which is basically, if you make it out of twin lead, it's basically just a single band J-pole. It suffers, as far as we know, it suffers the same problems as the regular J-pole. I just want to stop the rumor that just because you connect the top, if you make it out of twin lead, because mine floats and this piece floats, but if you connect the top, we don't see any difference either in simulation or performance. So the idea, whoever came up with this idea, this gives 6 dB gain. I think they were referring to the 6 dB gain versus a rubber duck. But so does any J-pole. So just don't get fooled that this gives 6 dB gain. To get 6 dB gain, we found it takes quite a bit. It really takes 2 elements in a collinear configuration to even achieve close to that. And that's a lot more elaborate than this. That's a talk I can give later on. Okay, so how did we do this? Here's our magic trick, if you've ever read our article. Not magical at all once you get the article and present it, because, I've always wondered about this. And I was, when did I come up with this idea? How old was I? 2003, so I was 45? No, 35. I was almost 40 years old when I came up with this idea. Yeah, let's see, that's all right, 35, I was 38 years old. Yeah, I was 38 when I came up with this. And you think about it, it's sort of one of these ideas, you sit at work and say, why can't I come up with one idea in my life that I could make successful? I was an engineer working on chips. I was a small part of a big project. Why can't I come up with something? And I guess this is it. I came up with something and I kept it. But yeah, it's actually pretty hard to come, these days with all the sophistications, it's actually pretty hard to come up with something really innovative that can really contribute. It's not that easy, but this was one. So anyway, I came up with this idea because these folks all came up to me and said, Ed, could you ever solve this problem? It's got to be simple and it's got to work and it's got to be cheap, right? Knowing hams, it's got to be cheap. This is a pretty good solution. Again, we've shipped over 25,000 of these, and I don't know how many of you folks have made them, but you can make them if you like. So here's the concept behind it. It's still, we take the normal J-pole and break it up. Now, remember I said, here's the matching stub. Here's the part that goes from the 0 ohms, goes to high impedance, and at VHF, it would have been normally a straight line here, and it would have been the half-wave radiator. So if you add all this up, 17, 4, 11, it'd be 37, 38 inches or so, half-wave. But what we do here is at UHF, the matching's not the problem. Right, at UHF, remember I said that anything that resonates typically at its fundamental will also resonate at its third or odd harmonics. So a 150 megahertz signal will also resonate at 450. So that's what this stub will do. It will match the impedance from fairly low to high up here, whether it's 2 meters or UHF, or 70 centimeters. It's going to do it. And the reason why it does it is at 2 meters, it's a quarter wave, right? Imagine a quarter wave, 0 here, and then impedance goes up like this. At 3/4 of a wave, that's a UHF, it will look like this. It will take a quarter wave there, up here, so it won't go all the way up. And then it needs another half wave. It needs you kind of have to see it. It needs another half wave coming up like this. So remember, every time you add a half wave, you've gone to the same spot on the Smith chart. So what that says is this will resonate at, if you design it right, 145, but also at about 445 at the third harmonic. And by the way, also at the fifth harmonic and the seventh harmonic. So it matched. The matching's not the problem. So once you get it matched here, at UHF, it would like to see, look into here, it would like to see about 11 or 12 inches, a half-wave radiator. But the original antenna saw 37, 38 inches. Well, that's not a half-wave. That's a half-wave of 2 meters. So in a regular antenna, the UHF signal will do a half wave here. And that's right, but it will have to continue. The current that's driving that piece of wire, it has to continue because it has not been disconnected. When it continues, that's what causes the wave. The current continues, so it's going to pull the wave up. That's what's causing those little 4-leaf clovers. The current continues. If it stopped, it wouldn't do that. So how do you stop it? Well, at UHF, you would like the current to come up here and exactly half wave and stop. It's as if the antenna was not there. So if this were not here, this whole top were not here, this will work fine as a UHF antenna. How do you electrically stop it? Not physically. Physically, we stop it, then we can't get the 2 meters working. So back to this quarter wave stub thing again. You get a quarter wave stub, which in coax now will be about 4 1/4, 4.5 inches. In air, it would have been 6 inches. But because coax has a velocity factor of this RG174, about 0.8, 0.7, 0.8, it slows down the speed of light by about 30%. So it turns out quarter wave at UHF is about 4 1/4, 4.5 inches, somewhere around there. You short it at the top. If you short the piece of coax at the top, well, at a quarter wave, it's going to be a high impedance. Maybe not infinity. I'll show it to you later. It's not infinity, but it's in the thousands of ohms, much higher than 50 ohms. So as far as you're concerned, if you drive this with a UHF signal here, 50 ohms, it sees 3/4 of a wave matched up here, it sees a peak. It drives this half wave piece, which is just right. At UHF, it shouldn't see me. It doesn't see this electrically because it's a high impedance. It stops. The current stops. We're good. Half wave. At VHF, of course, at VHF, this is a quarter wave stub, not a 3/4 wave, but a quarter wave stub. And it doesn't see this piece. It just sees this whole 11 1/4, 4 1/4, and 17 inches all added up as a half wave at VHF. I think if you add that up, it's something like 37, 38 inches, which is just right. That's how it works. Up to this point, any questions? Have we lost everyone?
I raised my hand a while back. Ed.
Oh, you did? Oh, I didn't see you. Yeah, go ahead, Steve. Go ahead.
I'm trying to be proper and raise my hand. Hey, this is awesome. I really get it now. The question was, how about, what came to mind is, you know how the Hustler whips, the ham sticks are? And you can put a metal hat on them. Was that kind of how the arrow works, sort of that type of design?
No. The Hustler is totally different. The hat is just to lower the resonant frequency.
Okay, gotcha.
Yeah, that's totally good. The Hustler, the antennas are just coils at HF. Yeah, totally different grids.
Right, gotcha. The question was, here's the one that got me is, I bought an original American Legion J-pole with the little wire on the side. That's an interesting rig. I bought it originally from QFO, man. It was amazing. That's how old I am.
It works pretty well, but that's a pretty lossy. We looked at that. The way they couple it at VHF is pretty lossy. It works, but the reason why it's so broadband, because I've got those. Obviously, we've bought these. The reason why it's broadband is it's lossy. So if you compare the American Legion with our antenna, and a lot of people have, ours does work a lot better, a few dBs.
Yes, yours is way efficient. I'm
yes,
I got a original 220 American Legion J-pole. It's interesting. It's an interesting.
Yeah, that coil, that number 14 wire they wrap around it to couple it. It's not designed to operate up at those high frequencies, so it's pretty lossy. It works. better than nothing. See, what we found that if you can couple it to twin lead 300 ohms. Why 300 ohms? Because it's only a 1/4 inch spacing. It acts as a great transmission line at UHF. If you do 450 ohms, that's 1 inch spacing. That's great at HF, even acceptable at VHF, but not at UHF. The spacing's too wide. And the other thing is, you notice we directly couple here. There's no coupling. If you guys are familiar with the American Legion, they use a coil of wire to couple it. And it's number 14 wire, nothing special. It's what's called the loss tangent. The loss tangent of that material is too high for high frequencies. So yeah, you'll find that ours works. We've matched it side by side. Ours does work better because we couple it directly right there, right at the bottom. So here's a roll-up version of it. A student of mine came up with this 3 or 4 years later, saying, "I like the backpack. Is there any way we can make one that can be all in one twin lead?" Because in this one, you have to solder this on and everything. So we found a way where you get it in one lead, you clip it, and you put heat shrinkable tubing, and it holds up. It holds up very well. And by the way, if you take the dimensions of the roll-up again, and you take the dimensions of the DBJ1, which is designed to be put into a PVC pipe, so it's more durable, what's the difference? It's about 2 inches. If you measure, it's about 2 inch difference.
And that's because of the PVC pipe?
Right, because remember, the PVC pipe slows down the speed of light by about 3 or 4%. So if C equals F lambda, instead of using 3 times 10 to the 8th meters a second, you use like 2.7, 2.6, 2.7. So the dimensions will just be a little bit shorter in the end.
So is there a little bit more gain on the without using the tube? Is there a little bit?
No.
Same thing?
No. Not if you use, that's a good question, Jack. And not if you use the Lowell's 23990. We tested this. Yeah,
the very thin wall.
It's called the loss tangent of a material. And what is the loss tangent of a material? It's how much your RF energy heats up the material while going through it. So that's a spec called the loss tangent. And you think, wow, how do you measure that? Actually, pretty simple. Without real quantifying numbers, all you do is take some of that material, put it in a microwave oven. You guys may have heard of this. You put it in a microwave oven for a few minutes just to check it out. If it gets warm, it's no good. That means you're heating up. That means your RF heats up the material. You don't want that. You want RF to go through it.
Interesting. Okay.
The 23990, we tried all the other ones too. You don't want to use Schedule 40. That is measurable. Not significant, but it's measurable.
It's a Lowe's 88, what is that?
It's 23990. I've got plenty of it, Jack, if you ever need any. Mel can come pick it up. I pick it up wholesale from them because I pick up so much of it. Mm-hmm, mm-hmm. So we tested Maynard's, we tested Home Depot's, and they're all about the same price. So it's not a matter of price. It's just a matter of RF. So the thin stuff, Lowell's works very well. We can't measure any losses. And it shows it. Stick it in a microwave oven for 20 minutes and it's going to get warm. So, it's pretty decent material for RF. And again, not very expensive. So, okay, we notice the dimensions and the pipe we already mentioned that. So here's the actual spectrum graphs out of this is out of an Agilent analyzer, 8591. See, here's a perfect example of a measurement we did. Here is the standard 2-meter J-pole, the 2-meter version made of the same twin lead, but we use it at UHF. So here it is. This is a parking lot, empty parking lot, 50 yards away or so. But it's all relative. So here's where it is, about 2 dB over this point. And yet, when we use our version of the J-pole with that little decoupling stub, it's quite a bit of difference at UHF. It's about 6 dB. 6 dB difference, because that's 10 dB per division. So that is about 4 times more. But it does work, even in measurements. In fact, here's a chart of it. Here is an official measurement, 3 different days, 5 measurements on each day. You have to do this with antennas because things change, humidity changes, temperature. You got to, one measurement one day, if you guys are RF engineers, is not good enough. You better make sure you wake up the next day and measure it again, that you weren't dreaming or something. Because I've had that where I said, I swear this was like this, and I couldn't duplicate it. So you have to be able to duplicate it as a general rule. 3 different days and 3 different conditions. And each time you should measure it, I think 5 times and take the average, because again, at UHF, you'll see the thing fluctuate just with time, half a dB here, depending on whether the fog rolls in, the fire smoke and stuff like that. That will make a difference. So here's what we did. If you actually quantify the measurements as a relative measurement, quarter wave mobile, this is at relative performance. Okay, this is just at VHF only. Minus 24.7 dB for quarter wave mobile. A rubber duck in a similar situation, similar distance, would be about minus 30.5. So it's about 6 dB difference. So at UHF, a rubber duck compared to like a good quarter wave mobile will lose you about 6 dB. You guys probably notice this, right? That's why you have the little mag mount, quarter wave on top of your car, and it works much better. Very noticeable. It's about 6 dB noticeable is what it is. And then a J-pole is a little bit better, minus 23. It's minus 24. Now you've gone up. It's minus 23.34. It is measurable. It's not significant, but it is measurable. It is a little better. But again, it has no radials and doesn't need a lightning arrestor, but it is 3/4 of wavelength tall. But I think in most cases, a 3/4 wavelength tall antenna is not that inconvenient compared to radials. I think radials you can't hide, right? A 3/4 wavelength, 2-meter J-pole, you can fool in your condominium that says it's my flagpole, right? And just put a little flag at the end of it. Not so sure you can do that with a ground plane. It'd be harder to convince.
Yeah.
Right? So, and then with the dual band J-pole.
Ed, I think Doyle has a question.
Yeah. Go ahead.
On these measurements, what kind of antenna were you using as your reference antenna?
Oh, this is it. No. Oh, yeah, on the analyzer. Oh, it's just the analyzer antenna. It's one of these, it's kind of like
one
oil.
of those cage things?
No, we did not use one of those. I know what you're talking about. It looks like a cage antenna. No, I didn't use that. It was just a standard rubber duck antenna. But it was constant. It was the same antenna. Yeah, okay. I know what you're talking about. It's a standard National Bureau of Standards antenna to test gain. Yeah, we've got one of those, in fact. No, we did not use that. Too inconvenient. These are all relative measurements. So if you use our dual band J-pole at VHF, it's pretty close to a standard J-pole. I think it's measurable where you lose a little bit on that stub, but not significant enough. There's 15 measurements here on 3 different days. So I'm pretty confident that these measurements can be duplicated like this. You do lose about 0.1 dB using my dual band antenna at VHF, because you put that little stub, it's going to lose something, and it does. It's about consistently 0.1 dB, not significant at all. Compared to, you gain back 8 dBs at UHF, because here it is, the bottom chart here. Here it is, minus 38.8 for a standard quarter wave. That's our reference. A rubber duck loses about 3 dB at UHF, sometimes less. I've actually noticed some really good UHF rubber ducks, especially the ones that come with the radios. They kind of match it to the chassis ground, because now you can really use that chassis ground because it's approaching a quarter wave. See, at 2 meters, you can't. Best thing is to get a little pigtail, 19 inches, to improve your performance. But if you don't do that, and you have a regular handheld handy-talkie, you can actually tune a pretty good quarter wave rubber duck. If you tune it just right, it would be better than minus 3 dB. You probably get it down to 1 dB, because I've done it. But typically, you might lose 2 or 3 dB. The standard J-pole, if you use a VHF J-pole and at UHF, you lose quite a bit. Again, you lose about 5, 6, 7, 6 dBs at least. You can see that minus 38.8 compared to minus 45. You definitely consistently lose out. But if you put that little stub that I've been discussing, not bad. You get most of it back. See, minus 38.8, minus 39.9. Again, you don't quite gain it all back. It's like consistently 0.1 dB. Again, this is out of 15 measurements, so we're pretty confident that these are true figures. It isn't I don't believe it's measurement error, because we did this quite a bit. Yeah, it's consistently about 0.1 dB, but that's not much. Remember, it was 6 dBs. It was 6 dBs here, or here. It's 6 dB. So you gain a lot of it back. Maybe not all of it, but a lot of it back. And I think people have used this antenna enough now to say, oh yeah, it works. It definitely works. Okay, here's our lab. We don't even use this anymore. This was taken about 10 years ago. Now, you know what I use now? I'll tell you what I use now. I gotta admit.
Yeah, is that in Nick's shop?
What?
Is that in Nick's shop?
In Nick's shop?
Is that in Nick's shop?
No. That's at school. That's
okay,
at school.
sorry.
That's an 8753 there. I use one of these nanos. I gotta admit, man, this thing. Do all of you guys have one of these for $50?
No, what's the brand on it?
Nano, Nano, Nano VNA. I see some of you guys. Raise up your hands if you have one.
I have a rig expert.
Oh, you gotta. This thing for $50, $60, up to 1.5 gigs.
Wow.
Has a Smith chart. In fact, let me turn it on. You can see it. You guys you've heard of this, right? You guys have heard of this, haven't you?
Yeah.
Yes.
It's just a digital oscilloscope, right? Is that
No,
what it is?
it's a network analyzer.
Oh, it is. Okay.
Here.
Yeah,
You see the Smith chart on it. See the Smith chart on it?
Yeah.
And it goes up to 1.5 gigs. You fully calibrate it. And, sure, this one goes up to 6 gigs, but unless I'm working at 5 gig stuff, I don't need this. Most of my ham stuff can be all handled by this. True 2-port network analyzer. You cannot.
Yeah, they get really good reviews.
Yes. It's
Yeah.
They're about $50.
Hardly any higher praise could come.
Dude,
That's
I need
right.
one of those in my stocking. I need one of those in my stocking, Ed.
Oh, absolutely. Well, QST reviewed the smaller version of it. Get the 4-inch one now. By the way, this is out. It doesn't cost much more. It's like $10, $20 more. Get the 4-inch one's touchscreen color. It's well worth it. It's a little easier to work with compared to the little one. So this one's out. And by the way, did you hear they got the Spectrum Analyzer version of this? Have you guys heard about it?
No.
It's a 1.5 gig. It looks exactly like this, but it's a 1.5 gig Spectrum Analyzer. So it was designed by a group in Germany, university group in Germany. They've worked on this as their project, and now it's a product. It's pretty cool. For the money, it's amazing. Absolutely amazing. I'm pretty impressed. It changes the way we look at ham radio. So here, we're ending up here. See, here's the stub. People question, how is the stub? So this is on my 8753. See, it's interesting. This analyzer was made 25 years ago. So it's not that we're doing anything new. We had color and all this stuff, but it was $80,000. The difference is now you can do the same for $50. That's the main difference. So here it is. The stub is not at infinity at 445, but really high. Good enough, right about there. It's good enough. And of course it goes all over the place in the other frequency, but at resonance it's pretty high. And same thing there. I put my hand around and everything. It's pretty stable. At resonance, it's still very high. It'll do other things if I put my hand around it, but it's very stable. And here's a piece of, here it is at 146 megahertz. You figure, what does it do at VHF? It looks like that at 146. And a piece of wire kind of looks like that. So you figure, yeah, it could pass for a piece of wire. It's probably a little loss here, but it could pass. It's good enough. And see, here's how it hangs up in my house. It's end-fed. It's a lot easier to mount. If this were a ground plane, it would have radios. If it was a half-wave dipole, this would look like a mess. It would have to come up, arms stick out. It'll torque, which means it won't have a wind load. And you'll make a dipole. It wouldn't hold up as well. It wouldn't work as well because the coax will have to run down, and it's parallel to the antenna. It will interfere with the pattern. You might get the SWR down, but it will clearly interfere with the pattern like that. The feed point doesn't interfere with the pattern. It goes right up. Very efficient.
Yeah.
PVC pipe lasts you years. Yeah.
Question about that. I've seen people that they'll use metal hose clamps. No way. I use PVC, like the plastic PVC type hose clamps sometimes to mount them to pieces like that because you're down there in the stub area, right? They're going to interfere with the antenna, right?
No. I got coax in here.
Yeah, I'm just talking about if you're mounting it, you're clamping anywhere down near the bottom. Aren't you going to do something bad if you have a metal clamp down there?
No.
No, you have about 6 or 8 inches
I've got
on
6
the
or 8
bottom.
inches, yeah. I've got 6 to 8 inches in the bottom. If you look at the antenna, the way we make it, yeah.
Because I strap it with 3/4 inch pipe straps.
Yeah, no problems.
Yeah.
Yeah, the actual antenna, the way we design it, starts about here. It's
Okay.
about 6 to 8 inches, that's why.
I don't go anywhere above that though. Yeah.
Yeah. No, actually, you can't even look because luckily it's at the low impedance point of that transmission stub. As you go up a quarter wave, then it gets really sensitive because it goes high impedance. Yeah, you can spare 6 to 8 inches easily. With not a problem.
Cool.
So
Thanks.
here's our roll-up version. You guys probably know this. We include it with a 6 feet extension, no charge because we get these custom made with a male BNC and a female. This way you can just hook it up and get the extension. We include all the adapters with it, mainly because we buy it by the thousands. We literally buy these by the thousands to get a price cut.
Wow.
So here's another talk. If you like what I just gave, I give another talk on this, how you get gain out of a UHF J-pole, like 4 to 6 dB. So then we started to patent these because people start copying them. Now, this is an interesting concept. And then, of course, we have the tri-band one, which I don't know how many of you folks have the tri-band. We came up with this clever scheme of how you can put 220 coils in there without affecting the antenna. That's another talk if you want me to give a talk. If you guys, Jack, if you run out of guest speakers, just give me a ring. If I'm not busy, I'll be glad to get on.
Would you guys like to hear from Ed again?
Oh, yes.
Yes.
Well, no, you gotta have, of course they're going to say, they're in front of me.
No, you want to do it again you got time in November?
No.
Okay.
Oh, I might now that I don't have to teach that class, I might, yeah. Well, you can book me for next year, certainly. I know I'm free next year. November, I've got to check on. And in December, I don't give anything. I'm just too busy doing family stuff.
Yeah, so maybe around February or so?
Yeah, sure. Yeah, we just
Okay.
Because with COVID, I don't know what my Christmas plans are now. Because you usually get family stuff, but I'm not going to have that. I got a good excuse now to stay at home.
Yeah.
Usually I don't. I go, okay, fine. We'll drive up there. But yeah, this year I kind of have an excuse.
So yeah, I've got a couple of your tri-bands, and they.
Oh, you do?
Yeah, they're good antennas. I've had one of your the dual band, the original ones, up on my office, my real estate office, up on the roof on the peak, and it's I had the smart thing. I used non-metallic, but I took some gray paint, kind of painted it. Now I realize I probably shouldn't have done that. But.
No, you can do it. If it's a thin coat, it will. You can probably measure that it lowered the frequency, obviously, because you're making it heavier. Therefore, you slow down the speed of light. So it will change. Yeah, it's got to be non-metallic. If it's metallic, all bets are off. But if it's non-metallic, most paints have a fairly low loss tangent. So if you paint it one coat, you can probably measure how much it lowers the frequency, which means that translates to how much it slows down the speed of light. But in terms of how much loss does it get, it's not major. One coat is fine. Yeah, it'll probably lower your resonant frequency by 100, 200 kilohertz.
In the mail.
So those analyzers are not really $50 anymore.
Oh, they're not on sale anymore? Was that just an introductory price?
Yeah, I think they became popular, just like everything else, the prices have gone up. But they're still, for $100.
No, R&L Electronics, they're not selling it for $59?
I don't see anything that has the nano BNA at $50 right now.
Yeah, I was looking at Amazon too, and they're all $100.
Okay, $100 now. No,
but even the little one that I purchased a while back, that was the 520, the one that MFJ bought, right? There was a company that's making a little one that was kind of like the nano BNA. And MFJ
no, it's nowhere close to. It's nowhere even near it.
Yeah, right. But even those are $250.
Yeah. No, these are a deal. No, yeah. R&L Electronics. I bought 3 of them because I wanted to use them for raffle prizes. They were $59. It was shipping and everything. R&L. Go to QRZ.
For your next party, Ed.
Yeah. You guys come to our next party. We'll raffle one off. Okay. We'll make it a door prize. When COVID ends.
There you go.
Good luck.
Good luck. Yeah, that might not be. It won't be this year. It'll be next year.
You're right. They're $60.
Right.
Oh,
yeah. I just see one right on there.
R&L Electronics.
R&L Electronics Nano, the Nano BNA H4, and it is in stock, and they have them here for $59.95.
Go buy it. It's a deal.
I see one on Amazon for $54.95.
Yeah. Tell them Ed Fong sent you. Yeah, I like it. The thing goes up to, if you calibrate it right, it will go up to 1.5 gigs.
Don't they come with a little calibrating?
Yep, they come with a calibration kit too.
Yeah.
hey, for the money, can you, you guys know Frank Layton and Nick Casario at CountyCom?
Oh, CountyCom. Yeah.
Yeah. Steve knows them. A lot of folks know.
I know VOA.
Yeah. You know what? We used to laugh at this, Frank does. Can you imagine 10 years ago if you were up at a repeater site and we didn't bring up a network analyzer. Too heavy, right? You bring it if you need it, especially if you had to tune a cavity. Can you imagine if 10 years ago you go up there, oh, I think this cavity's off. Because it's the repeater's having descents or whatever it is. I wish we had my VNA over here, and you just I just happen to have one in my pocket. Here it is. Can you imagine? You would just fall on your face.
Imagine bringing a Cushman.
Right, and a Cushman's not a total VNA. If you bought a true VNA, it would be real hassle. Can you imagine now taking that out of your pocket? Here, let's go tune. I have tuned duplexers on this thing. It's fine. It's works as well as anything I have. So I love it. And again, we give them away for raffle prizes. So yeah, $59.95. You can't afford not to have one. It's better than any antenna analyzer because it's a network analyzer, 2-port. So you can tune duplexers with it, and it gives you Smith chart readings.
We have a lot of folks that like to use the Wolf River Coil vertical for portable use in our groups, and so having a small analyzer like that is it's such it saves a lot of time when trying to tune that in the field real quick.
Yep. Hey, you must have saved with COVID at least $60 on going out to dinner in the last 6 months, right?
Save that a weekend lunch.
Right, you save that. I'm just going to go buy one of these VNAs. So anyway, I really recommend. I don't have any stock in the company or anything, but boy, I am impressed. Touch screen, color, yeah, you can't beat it. Anyway, so here's 220 radios. People wonder why did you add 220? The reason why we did the 220 thing was because FEMA uses 220 a lot for packet, and then people say, well, okay, I'm not FEMA. Well, next time you think about buying a dual band radio, think about these tri-bands. And Steve knows we give away these at FARX. These are the tri-band mobiles. By Radio Oddity, $99. They'll cover 220, 2 meter in UHF, BTEC, and then, of course, the BTEC tri-band, little handheld. In fact, that price is obsolete. You typically can pick up this tri-band UV5 times 3 for $40. So that's a good reason why to get into 220.
So you're selling the tri-bands for $40 now? Aren't they about 60?
Oh, the antenna. No, I'm talking about this radio here.
Oh, I see.
Yeah, the antennas are still 60. Yeah, they're still 60.
Which radio is $60 now?
This one. This handheld, it looks like a Baofeng UV5, but it's a UV5 times 3. It covers 2 meters, 220, and 440.
The only the main oddity with it's actually not a horrible radio. The main oddity with it is it comes with 2 antennas. It does not have it does not have a tri-band antenna.
Did Ray just say a Baofeng? It's not really that horrible. Did Ray just say that?
Well, that means it's mostly horrible. It's just not all horrible.
You have to say Ray is usually a negative to Baofeng radios.
Not a huge fan.
This is a special moment.
Yeah,
hey,
but they come with 2. They come with 2 antennas. You actually it does not come with a tri-band antenna, which is kind of strange.
You know why? It's actually hard because it's not harmonically related. Just like you see my tri-band antenna.
Yeah.
You cannot use the VHF, UHF portion to bootstrap on it. You have to have a separate resonator. And that's what we did it with our tri-band. It's a totally independent resonator. It's not like you can take advantage of the third harmonic or anything. So to build a good portable tri-band antenna, there's only one way that I know of to actually have 3 little resonating coils in there.
Yeah.
So yeah, that's true.
There's not too many tri-band handheld antennas.
There isn't. The reason why is it's only the United States that has 220 as a ham band. The United States and Canada.
Anytone has a really nice tri-band radio as well.
Yeah, the 878? It's called the 878, right?
There's the 578 as well, which is their new mobile, that mobile radio, which is pretty nice.
Yeah.
Is the BTEC Mini that you have up here for a little little portable radio, is that a pretty good little radio?
Hey, $40.
No, the $128 one.
Oh, this one. Oh,
the
yeah.
little itty-bitty one.
I use that one. Yeah. I think it's pretty good. Yeah. It's got a good front end. It does draw, and because of that, it does draw, 400 milliamps on standby receive because it has pretty good bulletproof front end.
Okay.
And by the way, these two are basically the same hardware, I've noticed. I've got both of them.
Mm-hmm.
They come with the programming cable and everything. It's the same hardware. The software is a little bit different. They're right. I think the software is a little better on the VTech than on the Radio Oddity, but they're both pretty good. I've used both of them, and Steve, have you won one of these yet? Whoops, no audio.
Sorry, I'm buying myself an analyzer.
Oh yeah, but do you have one of these? These Radio Oddity radios?
I know. I got
You don't? Okay.
County Com radios. Remember, I won one of those, man.
Oh, which one did you win?
The HF radio, the receiver, man. The GPS receiver. You know, kind of in front of me. But,
I forget which one you want. Anyway, we've given, at FARS, we've given away about 20 of these now. People really like them.
The little radio auditing.
Yeah, I pay like $100, but that includes tax, shipping, and everything to your door.
And they're itty bitty. They're tiny.
Yeah, they're tiny, 25 watts. I don't like to run them at 25. Just, run it normally at 10. And then, if you really need to, hit the 25 watt high power because it's got a little fan in it. And if you talk a long time at 25, it gets pretty warm, especially on a hot day. 10 watts is fine, right? Right? Just face it. You could talk to most folks on 10 watts.
You match that together with like a little lithium iron phosphate battery, and you make a really cool little go kit with that.
You could, but these radios are kind of high performance. So the problem, I don't like them as a battery operated. They draw about 400 to 500 milliamps on standby.
Oh, I see.
The reason why they do that is the front end. In order to get a linear front end, you have to draw current. A good, a fairly bulletproof front end, you have to draw current. And so they're a little high, but, at my base, it's great. 500 milliamps is nothing. Yeah, maybe with a big battery, 500 milliamps is nothing.
Yeah.
But they do draw, and I know why they do it. There's just the math. It's IC over VT. It's the transconductance of the front end. And then you can plot the linearity of it. The more current you draw, the better the linearity is. So they have to do that. I mean, there are other ways. You could put tuned circuits. You could put track tuning, but nobody can put track tuning on a radio this wide. 2 meters, 220, 440. They could put bandpass filters, but they cannot put narrow band tracking filters. Then you can reduce, because then you tune them out. Then you can reduce the current, but nobody can, at a reasonable price, you can't do that.
That's pretty cool.
It is. Oh, do I have?
So of those two radios, do you think the little VTech Mini is better than the Radio City, or are they about the same?
Oh, between the two, the hardware's the same.
Oh, okay.
The hardware is exactly identical inside.
Okay.
They just the interface is a little bit different, and then the software. I think they put a little bit more time in the VTech. It's pretty minor. Oh, I'll give you an example. I like the VTech software. It's got 4 rows of usable text that you can text, and you can use that as 4 independent VFOs or memory banks. 4 groups. You can use it as 4 groups. But you can also have the 2 group, and then the second row you can have as alphanumeric from row 1. In other words, row 1 you can put the frequency, and then row 2 you can say this is a FARS or whatever, Grizzly Peak or whatever. And then the third row you can have another channel, and then the fourth row you can call it a name. The Radio Oddity, I noticed you can't do that. It's just strictly 4 rows of different VFOs. So it's all in the software the way they've written it. But performance-wise, it's all the same. And all of them, you can change the color of the screen from purple to green to red, and that's kind of cool. Mm-hmm. And it comes with a cable, comes with the software. $100. That's right, Jack. That's like 2 lunches. 2 lunches.
Yeah.
2 good lunches. That's really good lunches. But yeah,
when Georgia and I were looking at them, I got one of the original little VTech for, I think I paid $65 or $90, or I don't know what it was. But it doesn't, the software is not very good. It seems to sometimes fail. So I have it in a little box. I can't remember the brand of it. Hang on.
Oh, I know about the software. Once you get it going, it's okay. Yeah, it's shaky. Jack, I know about it. Yep.
Yeah, you just use Chirp.
Always use Chirp.
Use Chirp, and you buy the dongle from RT Systems.
Yes.
Yeah.
So it's a smart dongle, because the one it comes with, the problem is the one it comes with. By the way, here, I got
this one, George.
Oh yeah.
And it doesn't. It's not very stable. It seems like it's starting to fail. So Wasn't much. It was their first version. I made a
No,
little
the
box.
reason why it fails, hang on, I'll show you. The reason why it fails is it's an old dongle without the smarts, like these. Here.
Oh,
Here's one. There was a sale on these. You buy 5 of these and you get a free programming cable. Forget the free programming cable.
Yeah.
It's not a smart cable. You got to load the drivers. And every time you boot back up, you got to reload the drivers. So that's why I have a bunch of. Anyone wants one? Come up. I'll send it to you free. If you buy these 5 at a time, it would come this free cable. The free cable was useless. Not useless, but such a hassle. What you got to do is you got to go to the McLord site, and they'll show you the cable where you've got the drivers built in the dongle. So when you plug it in, it loads all the drivers. Then it's convenient to use and it works all the time. Yeah, Jack, I know what you mean. I went through this. I was trying to figure out what piece of junk. No, if you buy the cord from RT Systems, they've got the drivers built into the dongle. You plug it in, it's in.
They use the
okay.
real TDI serial chip, so they use
Right,
the
right.
real deal. They actually paid the money to license the real thing, whereas those other ones don't, and
They don't, right.
Yeah,
So you
they're
have to load the drivers in from the computer.
Yeah.
And then what I noticed is, wait a moment. It won't even recognize it if you unplugged it and plugged it into a different port, because that's all registered as you load the drivers. So the great thing is you buy the RT one, it has all that intelligence built in. You plug it in, you hear beep like that, and done.
that was the one that we originally bought. George and I bought one of these.
I remember those.
Yeah.
And we had to change the mic, the little mic element in here.
I remember the mic. Yep.
Oh, it was bad?
Yeah. Mine was bad. Mine worked for all of 15 minutes and then it quit.
Wow. So they've gotten a lot better. You guys must have been the early guys that bought this.
Yeah.
Yeah.
Yeah, we jumped all over it. I thought it was the coolest thing ever. A bunch of us bought them, and
You bought them.
It's kind of funny because you could put it in a little bolt box, and it was real handy, a little radio, and
You bought them too early.
yeah.
Because now I've never had a bad one.
that's
They're
why
all,
we're called amateurs.
yeah, I think you guys bought these when they were first introduced.
Yeah, it was a little BTEC. So maybe
Yeah.
I'll get one of those and put that in my boxes. I love having this little, little UHF.
Yeah. Now they work much better. Oh yeah, much better.
Okay,
I don't
that's
sell
fine.
these. You can go onto their site, go to Amazon, you can get these.
Yeah.
Okay, here's one thing we offer. I know Steve knows about this. This is the GP5 County Com radio.
Nice
I
radio.
have one.
You have one?
Yep.
Yeah, so if you guys ever need one, I get them from County Com because I worked on the single sideband detection on this. $65. Just don't tell Nick and Frank because it's normally about $100. It's about $100. By the time you do this tax and post, it's about $100. If you guys need them, I can get them for you.
It's a cool radio.
It is.
What is this one? Tell us about it.
It's an HF. We worked on this about 8 years ago now. HF also does low band, if you want to do low band 150 kilohertz stuff. And it'll go AM, single sideband, or CW. It uses the Silicon Labs DSP 22-bit. That's 22-bit DSP chip. It'll also do FM stereo. And it's got like 200 memories, but it's handheld. And for $65, it's a pretty cool radio for $65.
So what's the output of it? Let's see.
It's a receiver only.
Oh, I see. Okay.
But it does receive quite well. I guess it was a contract they got from the government that Nick and Frank had. So we came up with this, and it is a very nice radio for what it is.
It's pretty cool little radio. It's got an alarm clock if you need that.
Yeah. The only thing I don't like about it, because of the chip, it draws about a couple of hundred microamps on standby. If you turn it off, the
So it's kind of
clock.
a battery eater.
Yeah, the clock is on and some other stuff is on. I think they could have lowered the standby current on it. So if you leave the batteries in there for a month or so, it will go dead. So I don't like it. So you have to make sure if you're not going to use it, remove one of the batteries so it doesn't go.
Where's your application for that? What's
Ham HF. Ham HF. It'll do all HF. Single sideband, 80 meters, 160, 20 meters.
Just for receiving only.
And we designed it with a magnetic antenna instead of a electric antenna since it doesn't transmit. So when you pull out the whip, it will work fine as long as you're in the clear. It's designed that way. It does not need a long antenna. It's strictly magnetic. It's not electromagnetic because it doesn't transmit.
Oh, wow. Okay.
Yeah, so the 20-inch whip it has works fine.
Yeah,
As long as you're in the clear, you got to be in the clear.
So you're one of the designers of this. Right?
Yeah. So
I
if
did
you guys
not know that.
want,
That's cool.
just tell me, $65. Tell me ahead of time, I can get a bunch of them. But that's about it. And here it is. If you guys want antennas, I'll send it to Jack a spreadsheet. They're $30 a piece, whether like the DBJ1 commercial or ham, DBJ2 commercial or ham. We got the tri-band's only ham. $60. That includes the PVC pipe. So Mel can pick it up, or whoever comes up here or goes down there can pick up everything. Extra extension cables for the roll-up, they're $5. A lot of people request a BNC to PL259 adapter, so the roll-up can be used for mobile. That's
I could be a
$250.
personal UPS driver because I live nearby, right? And I can just deliver them to these guys in Morgan Hill, Gilroy area.
But Steve, how often you go down there?
Once
Oh,
in
we
a while.
can, Steve, we can work it out. If we get an order, we can put them up.
Yeah. Mel comes up here quite often.
Yeah.
Or else I can meet you guys in between. It's just that if it's a single trip, that's what, an hour and 10 minutes?
Yeah.
That's so long. You can meet in between, half an hour for each person. Yeah, because Mel, a bunch of people come on up.
I've got
So,
I sell real estate, so I got a real estate listing up that way, out in Sunnyvale.
Oh, okay.
So
Yeah,
I'll be
just come
coming
on
up that way anyway.
Yeah, if you go, come on up. So I'll just send you a spreadsheet. You guys can fill it out, and then I just need a summary. Give me a few weeks because we're really busy. Oh,
Good.
you would not believe how busy we are.
Are you doing the manufacturing at your house?
Yes, yeah.
You do it all there? Okay.
Yep. Well, we do a lot of the pieces in China. Some of the coax comes from China and all that. But the final assembly, and tuning, all at my house.
You did a custom antenna for me a couple of years ago for a scout camp. We got a repeater donated, and they had commercial frequencies, and you made me a custom antenna for that, which was really cool.
UHF or VHF?
Yeah, it was UHF.
Oh, really? I don't. I do a lot of these, so I don't remember.
Yep.
If you ever want one,
I'm going to need one of those too, for Scout Camp.
Yeah, just give me a call. They're cheap. The UHF, so I don't have the UHF one here. That's $40.
It'll be UHF GMRS.
Yeah. Just they're easy to build. $40. And if you come over here, I've got you get the PVC pipe for free because the PVC pipe is insignificant. I just don't mail it with it. You send it cross country. It's $14.90. So I tell people just go down to Lowe's, pick it up, slip it in. You'll save a lot in postage. But you guys are close. If you come here, I just give you the PVC pipe with the antenna.
Hey, there was a question by a couple of chat questions here.
Yeah, sure. Okay, I don't see that. Yeah, let me close.
Yeah, here's Brent, and it says, does the GP5 single sideband have a scan function?
Yes, of course. Yeah, it has a scan function. Yeah. So thank you very much, Jack and Mel. Even though he's not here to invite me. And
Radio right here, Ed?
What?
It's radio.
Yeah,
right
there's
here.
yours. Yeah, he's got.
Yeah, all charged up.
Question for you, Ed.
Yes.
On these antennas, is there any on the feed? I noticed there's no chokes or coils or anything like that.
No.
Is there? Okay.
It's a good question too, because we run a lot of tests on these. If you run it at resonance, so you'll see our antennas are pretty good in ham bands. That's all we're guaranteeing, a ham band only. You'll see that the SWR is pretty low on the ham band. So in a ham band, what we know is obviously if the SWR is a pretty good match, you don't need a choke. There's nothing reflecting. Yes, obviously if you go out and you start using this in a commercial band and basically using it in areas where there is not good resonance, you better get a choke because you don't want, especially if you're using a mobile, you don't want that power reflecting back into your radio. So we've done a lot of tests on this. And real RF tests with spectrum analysis. Does a choke help when the SWR is already low? Well, intuition says no, because what are you choking? You already have a low SWR. But clearly if you have a high SWR, that's a different story. Because I'll tell you, you start transmitting 50, 60 watts, and let's say your SWR is 2 to 1, so then you put a choke. Have you guys ever done this? It's hotter than you think. Right? You just work out the math. Even if you get 25% of it reflecting back at 60 watts, that's 15 watts. Have you ever held a 15-watt light bulb? So I've done this. Boy, 5 minutes of that, and you just touch that ferrite, it's almost too hot to touch. In fact, Dean Straw had a talk about that at Pacificon. People don't realize that. So you can crack ferrites, when you have bad SWR. So the ferrite serving its purpose is converting the RF energy into heat so it doesn't go back into your radio, right? The whole purpose is, no, choke shouldn't make your performance any better. It probably doesn't, but it saves your radio. Clearly it saves your radio. But it can't be that efficient because when you touch that choke, where did it get that heat from? From nowhere? No, it got it from your RF that's reflecting back that you want it to radiate into air. So what I tell people, why don't you just fix your antenna? If you fix your antenna, you won't need the choke. If your antenna is not working, yes, you better have the choke because you'd rather not blow up your radio. If it's a cheap Baofeng, you have no problem. Just go buy a new one. But you got your, 950 or you just bought your 7300, or I've got sitting in my shack a Pro 7, ICOM 756 Pro that got burnt out because of that. Yeah, then you should put a choke. Then you're protecting a $1,000 radio. But again, if you blow out your BTEC, not good, but it's not the end of the world. But I tell you, you buy your nice brand new IC 7300 and you burn that out, you don't feel too good about that. So yeah, then you put a choke, just in case. But you'll be surprised how hot that gets. That's what I noticed. Boy, I thought the thing was just choking, the heat dissipates. So we did experiments on this because I got a lot of time at school. You just do all these crazy things. When people suggest things like you guys, well, let me go try it out and see. Yeah, you can always simulate. There's some intuition, but let's try it out and see. Oh, you touch that choke, man, especially if it's kind of a small one, to dissipate 20, 30 watts. Let's say a 100-watt radio and you have a SWR 2 to 1 or 2.5 to 1. Oh, it gets pretty hot. Again, too hot to touch. Because I remember I was really shocked when I touched it. It almost burnt my hand. So that's what a choke does. So whenever you see antennas that have to perform well with a choke, that's a good hint. It's not a high performance antenna. It's good for
some of the InFeds, that you see the dipole antennas with InFed. Yeah. They'll have part of the coax is set up as a lateral, and then they put a choke on the end of it before you get to your radio to stop to end the length of the coax.
That's right.
To balance it. Yeah.
Hey Don. Hey, I didn't see you. Hey Don, how you doing? Turn on your mic.
Hi Ed, how you doing?
Oh, I'm doing good. Haven't seen you in a while. You're looking good.
Yeah, thank you. Definitely.
So Don, I know. So that's my theory on chokes. You probably do need them, especially if you do broadband and you go all over the place. Yeah, it could protect your radio. But a good working antenna should not need a choke. Oh, I'll give you an example. Do you get a X200, X50, these commercial antennas, cell wave. Do you see a choke?
No.
You see chokes on ham antennas. You don't see them in commercial antennas. Because if you need a choke, you're doing something wrong. That's my conclusion. If you're doing something wrong, rather than fix it, to dissipate the heat and fix it, that way with a choke, fix the antenna. It'll work better that way. Right, Don? Don would know. Don's a technical.
It sounds good, Ed. I got one question.
Yeah.
Unless I didn't want to interrupt.
No, you're a good guy. You can interrupt me anytime, Don. I've known you for
well, you're looking good. You're looking good, Ed. So is it strictly the spacing between the two elements that typically yields it for its VHF, UHF performance? What starts to happen or prevents it from being usable, say at 0 to 30 megahertz?
Oh, just the resonance.
Strictly the resonance.
Yeah. If in general, if you have a wide band antenna, the widest band antenna is what? A 50 ohm load. Right? That's the other extreme. Oh, it's low SWR everywhere, but it doesn't perform very well.
Sure.
And a high Q antenna, typically a high Q antenna in general for its size, for a given size antenna, you want a high Q antenna. That means it's very efficient at a particular frequency. And that's why in a loop antenna. Loop antennas for their size works quite well. And they're typically very narrow band because they're very high Q, but plus they're made of very low loss, tubing.
I see. Oh, very nice. Okay.
So typically a high Q antenna also says that you have typically lower loss, but of course narrower band. So that's why I'll give you an example. Some people, like Nick and Frank, make me this antenna for this frequency. How does yours work so well? We know it's pretty simple, not as big. I go, well, look at the bandwidth you're getting out of these antennas that custom make for you. They're not very wide, but they work really well. They're not very wide band. This is for VHF, UHF repeaters. Because typically if you buy a commercial antenna, it might be good for, 5 to 6 megahertz because of repeater use. So they're a little wider, but they don't work quite as well because obviously their Q is a little lower.
I see.
But as a general, I'm just saying this is a general. There are people, Steve Stearns will come back at me and say, but yeah, you're right. But as a general rule, there's exceptions. You can make a wide band antenna and still perform fairly well. There are ways of doing it, but it's not like a typical, here's a dipole and we're going to resonate it. No, it's not that. You have to do other things to it to make it wide band and perform well.
Okay, very well. Well, congratulations for sure on the J-pole design that you have. It's a nice setup.
Yeah, have you seen the tri-band one?
I have seen them over the years. With the pipe configuration, the white.
Right.
Yeah, I've seen them.
Those are very, very popular. People really like those.
Yeah.
So, Don, where are you living now? Are you living up here or down?
I'm down here right near the gentleman, near them in Hollister. Hollister's 5 minutes down the road. I'm in San Juan Bautista.
Okay.
Yeah, okay. It's nice. I'm right before downtown.
So here's one man I do see at Pacific.